Hey guys, so this is section 10.1 where we're talking about the enthalpy, entropy, and Gibbs energy of ion formation in solution, ions. So we'll start by looking at this real simple equation, hydrogen gas and chlorine gas being dissolved in an aqueous solution and forming the hydrogen ion and the chloride ion. This looks really similar to just the dissociation of hydrogen and chlorine that make hydrogen ion and chlorine ion. The difference is that they're aqueous here. That's a huge difference actually. One important thing that happens is that when these ions are in solution, they have a solvation shell. So for example, the hydrogen ion is going to form fairly strong Coulombic interactions with the water molecules because they're polar. And it's going to have this cluster of water molecules. It's in 3 dimensions in reality that surrounds it. Same thing with the chloride ion, and that changes everything. The process of forming these solvation shells is exothermic because we're bringing opposite charges close to each other. So even though it takes energy to break apart these atoms from each other to form the ions, energy is released when they're solvated. Specifically, if it's in water, it's called hydrated, but solvation is a more general term. It could be any solvent. We'll talk about water, but it applies to any solvent. The delta H of reaction under standard conditions for this is the delta H of formation of the hydrogen ion plus the delta H of formation of the chloride ion, both aqueous. Minus the heat of formation of hydrogen and chlorine, but those are both elements in their standard states, so the heat of formation of both of these is defined as being 0, so it doesn't appear down here. So for ionic species in solution, we need a reference point, a reference standard, and that has been defined as the hydrogen ion. So the heat of formation, the Gibbs free energy of formation under standard conditions of the hydrogen ion in aqueous solution is defined as being 0 for all temperatures. That means that the molar entropy under standard conditions of the hydrogen ion in aqueous solution, which is negative partial delta G of formation of hydrogen ion partial T constant P, is 0. And also because delta H of formation of hydrogen ion in aqueous solutions is delta G plus Ts, that's going to be equal to 0 too. So this is our reference point, our kind of bootstrapping ourselves up. Now that we have defined the reference point of hydrogen ion as being 0 for delta G entropy and delta H of formation, we can find these values for other ions relative to these. So what we do is we perform the reaction and we measure the heat of reaction, delta H of reaction for this reaction. We can find delta G for this reaction using delta G under standard conditions is equal to negative RT ln K. We can get K. It ends up by measuring the change in the conductivity of the solution. It's a pretty cool experiment, but basically, you measure the conductivity and measure the conductivity as time changes, and you're able to determine the degree of dissociation. Knowing the degree of dissociation, we know the concentration of the species present in the solution, which gives us our equilibrium constant. Knowing that, we know delta G. Okay, so now that we know delta G, we know delta H, because we measured it, that's Q sub P, thermal energy transferred at constant pressure. We can find delta S of the reaction, delta H minus delta G over T. So now that we have those, we can go even farther. So what we have is we've got delta H of reaction, which is equal to, we said delta H of formation of hydrogen plus delta H of formation of chlorine minus these, which are 0. But because we defined heat of formation of hydrogen ion as 0, the delta H that we measure for this reaction, guys, it's equal to the heat of formation of the chloride ion. We could do the same thing for bromine if we wanted to get the heat of formation of bromide ion or whatever. Also, because delta G of formation of hydrogen ion is defined as being 0, delta G of this reaction is equal to delta G of formation of the chloride ion. Now, delta S of the reaction which we get from these two values up here, is going to be the molar entropy of chloride minus half the molar entropy of hydrogen minus 1/2 the molar entropy of chlorine. These two we can look up. They're not zero, by the way, but we can look them up. And they're not ions, because what we're talking about here are ions. We're trying to get at the ions. So the thing we don't have is the molar entropy under standard conditions of the chloride ion. But once we get the delta S from these values up here, and looking up these values, we're able to calculate quite easily the molar entropy of the chloride ion. And something you'll see as you look at these values, the molar entropy of an ion in solution can be negative. That's because when they form these solvation shells, the entropy decreases, and something that's small and highly charged, like magnesium ion, beryllium ion, these things, they have negative molar entropies. But okay, so once we have that, so now that we have all these values for the chloride ion we got from up here by defining the hydrogen ion as being 0 for delta G of formation, now we can bootstrap ourselves up and get these values for other species. Let's say we looked at the dissociation of sodium chloride, solemn sodium chloride in water to make the sodium ion and chloride ion. We can measure the heat of reaction quite easily, which will be the heat of formation of the chloride plus heat of formation of sodium minus the heat of formation of solid sodium chloride. This we can look up. Again, it's not an ion, so we have no problem looking that up. We just got the heat of formation of chloride from our previous experiment, so the only thing we don't know in here is heat of formation of sodium, and there we go. Once we have that, we can get the delta G of formation of sodium, molar entropy of sodium in the same way that we just did, and there we go.